Hello, my name is Philip Tong, and today I'll be presenting the paper An Integrated Approach Towards Hillside Building Design for Automated Construction, co-written by Hans Christian Wilhelm. In this presentation, I'll be covering the research outline, including methodology steps, the background research, and the resulting design process, with a brief discussion of the implications. We'll start with the problem statement. The environmental qualities of urban hillsides often appear compromised and underutilized, due to the general response to sloping topography typically being informal settlement, high-end bespoke, or non-utilization altogether. In New Zealand, where several cities have complex topographies, low construction productivity is a major driver in the high cost of dwellings. Innovative construction techniques, such as prefabrication or automation, can potentially increase construction productivity. Finally, the requirement for denser urban models in cities has been widely acknowledged but lacks implementation on hillsides. As such, exploration into the hillside application of those innovative techniques seems best suited to medium-density housing. The literature review looks at three primary topics, starting with looking at principles of prefabrication, also looking at current applications of construction automations, and then also looking at principles of hillside design. With this in mind, this paper proposes that adaptation of existing automation-assisted construction practices to hillsides and the development of a design method that integrates the required site infrastructure can increase construction productivity on sites with sloped topography. The research is comprised of three main steps. First, establishing general typologies for hillside designs. Second, establishing typologies of techniques for construction automations. Finally, using the resulting typology research to formulate a parametric framework for design and siting of medium-density, low-rise dwelling structures suited for serial automation-assisted construction. The initial steps focus on case studies. From a mix of local and international hillside precedents, establishment of general typologies allows for basic knowledge of some design strategies for how the geometric form of the building could relate to the slope. The elevated typology, or stilt house, is a prominent response within New Zealand to the hillside condition. In combination with the fact that stilts have less of an impact on the site itself, requiring less earthworks, this typology has been selected. A similar analysis of construction automations is also developed, though this focuses instead on the technical qualities of each identified automation. In order to find the techniques best suited for hillside application, the most pertinent qualities identified are the mobility, or the ability for the automation to relocate itself, and the reach, or the zone in which the automation can work before requiring relocation. These two categories of analysis have then been overlaid with each other to develop three initial assembly strategies that incorporate theoretical automated construction processes. Starting with the sequential fabrication process, in which an initial structure is constructed on-site and then used to support a robotic crane. Further assemblies are then constructed to support modules moved into place. The second assembly strategy concept is the spine and unit process, in which a spine assembly is constructed first by a mobile automation, which then uses the spine to advance and continue building. The units are then constructed out from the spine. Finally, the funicular assembly process, in which a funicular railway system is used as a central point from which the automation works as it constructs the dwelling around it. This limits the dwelling to a relatively linear shape. Aspects of these strategies are selected for further development. The sequential fabrication strategy has the greatest potential for adaptation to a modular prefabricated system, while the spine and unit strategy has a better programmatic layout with a shared pathway for access and infrastructure. The resulting proposed strategy is based on volumes placed in a grid, angled by 45 degrees to the face of the slope to allow for better overall cohesion and to allow for better views from the outward faces. The volumes themselves are to be assembled in three stages. Initial foundation installation on-site, followed by on-site construction of a supporting framework, and then finally location of prefabricated modules. For the envisaged method of design, the strategy comprises two steps and a combination of parametric and manual design processes. Firstly, and the primary focus of this paper, developing a script able to determine possible sites on an input topography and generate a structure based on identified parameters. Secondly, manual manipulation of the output into a dwelling using qualitative criteria. The script here is understood as an analytical design method or tool which can be applied to other instances of similar environments with an output that allows for automation-assisted construction. The output from the script is not understood as an entire design in and of itself. The parameters of the script are developed from the decisions around the structural and design requirements, starting with the foundations. Due to the similarity to existing screw pile installation machines, it is proposed that an in-situ tracked automation can be used to install the screw piles. The capabilities of tracked machines to access slopes has been identified as optimal behavior on slopes up to 25 degrees. As such, this is used as an input parameter to identify where on the topography optimal construction performance is possible. The volumes are equally spaced in plan, with a gap in between. There are three main purposes to the interstitial space that is formed: connection modules between volumes that allow for households to be formed, or for light and ventilation purposes, or for the shared accessway and services. The volumes are arranged to have level differences in half-story increments, allowing for the possibility of split-level programmatic design. The volume scale is also derived from room scale, allowing for one large open room, or one large room in a corridor, or two smaller rooms in a corridor. To test the parametric design tool, a case study site at Shelley Bay on the Miramar Peninsula in Wellington, New Zealand has been identified. This area is likely to be developed for densified urban development and exemplifies the problems associated with hillsides as described earlier. Furthermore, the Shelley Bay development has also garnered criticism for issues such as a lack of affordable housing in public spaces. Following site selection, the actual scripting can begin. Visual scripting with Grasshopper and Rhino has been used for slope analysis and generating the geometry. The script begins by generating a topography surface from a set of contour lines and analyzing the resulting surface to find the sloped areas that are 25 degrees or less. From this, the point grid of previously defined dimensions is applied to those areas that can be accessed, showing where the volumes can be located. The floor plates are then created at those points and moved to both fit the half-story increments and moved up if they intersect with the topography surface. Once these floor plates are located in valid positions, the stilts can be generated, allowing for identification of pile locations. Finally, the floor plates can be extruded into the volumes of the modules. Once these volumes are generated, they are grouped into the larger overall clusters, and a scripted algorithm identifies a path for the shared accessway to follow. This pathway is generated from criteria including maximum vertical distance covered by the pathway and the number of units that can be accessed from it, and only uses paths that don't exceed the maximum stair pitch. At this point, the limits of the script have been reached and manual design takes over. The pathway is refined by minimizing the number of corners turned to allow for users to be able to see further along the path for a better sense of security. The volumes are refined through the removal of certain units, starting with removal of the units that clearly aren't feasible, followed by removing units at the corners of the refined pathway for better views from the path. Finally, the removal of certain other volumes is dependent on the next step, which is the laying out of the households themselves. The household units are composed of 4 to 5 of the generated volumes and are laid out manually. The clustering of households needs to account for factors such as vertical displacement between adjacent volumes to allow internal stairways to be possible. Manual identification of the household units is desirable as there are many potential qualitative factors alongside the quantitative factors. Given the limitations of parametric generation as a quantitative tool, qualitative decision-making is better suited as a manual process. Further considerations for design development include looking into space heights, multiple levels, or rooftop access. At the moment, the generated volumes only form single-story, single-height households. The design tool developed in this paper allows for parametric synthesis of an efficient modular approach towards hillside construction. The proposed automation-assisted strategy appears to have high potential within New Zealand, addressing the low construction productivity often found in hillside construction, while integrating the requirements for the automated process into the designed process. These characteristics are indicative of a design method with the potential to allow for better design and more efficient use of hillsides. Additional progress on the development of this design tool is currently looking at developing parameters for further scripting, gathering such parameters through architectural design at a household floor plan scale, and finding the common rules for floor plans to follow. The vernacular architecture of hillside settlements follows the concept of settlement as a pattern. In a similar sense, in this paper we are looking at developing a tool for site-specific dwelling and urban design, in a manner that is comparable to those hill towns that are grown over a long time. Thank you for listening.